You have picked a model for your project. Downloading it should be the easy part. Instead, the model page offers several files: FP16, Q8, Q4, AWQ, and GPTQ all claim to represent the same model. Some files are dramatically smaller. You may know this is called quantization, but that label alone does not explain what changed. To choose intelligently, we need to follow the bytes inside the model and quantize one tiny tensor ourselves. An LLM carries several kinds of numbers. The first kind is its weights, learned values stored in large matrices. Weights come from the downloaded checkpoint and stay in memory while the model runs. They dominate the static model size. Now watch what happens when a token enters model. The token ID is first turned into a vector of numbers called an embedding or initial activation. Each layer reads that vector, applies its stored weights, and produces a new vector. These temporary vectors are activations. The token starts the computation, but activation vectors are the numerical state that flows through the layers. The KV cache has a different lifetime. After a token has passed through attention, the model keeps that token's key and value records, so later tokens can look back without recomputing everything. Weights stay, activations flow, and the KV cache grows. Quantization can apply to all three, but your download choice begins with the stored weights. So we leave the temporary runtime numbers behind and return to the checkpoint. Zoom into one tiny weight tensor, and the enormous model becomes an ordinary row of 6 learned values. Suppose these 6 values are stored in FP16. Each position receives 16 bits, for 96 bits in total. Quantization does not remove any of these 6 positions. It changes how each value is represented. To see how, we first need to replace the continuous number line with a small set of allowed landing points. Our smallest weight is -0.82 and the largest is 1.10. The range is 1.92. 4 bits can store 16 different codes numbered 0 through 15. Those 16 points create 15 intervals. Divide the real range by 15 and we get 0.128. That value is the scale. The intuition is simple. When the stored code increases by 1, the reconstructed number moves by 1 scale size jump. Now that the ruler exists, we can use it to turn one real weight into a small stored code. Take the original weight 0.27. First, subtract the minimum, so its position is measured from the ruler's start, 70U. Divide by the scale and round to the nearest available position. The result is code 9. The file stores that small code. To interpret it, multiply 9 by the scale and add the minimum again. We reconstruct 0.332. It is close to 0.27 but not identical. That gap is quantization error. One value is useful for understanding the mechanism. Next, we apply the same operation to the whole tensor and see what the file actually stores. Apply the same mapping to every value and the 6 original weights become 6 codes between 0 and 15. The block also stores its scale and minimum. These two metadata values give all 6 codes a shared meaning. The code is the cheap stored value. The reconstructed decimal is an approximation produced when the execution path needs it. This is the basic mechanism behind quantization. Small codes replace expensive values, while shared metadata preserves their approximate numeric range. But smaller codes only matter if they reduce physical storage, so now we count the bytes. Now make that storage physical. Each Q4 code opens into 4 bits, which is 1 nibble. Pair 2 nibbles, and they exactly fill one 8-bit byte. 6 codes therefore occupy 3 bytes. Those 3 code bytes are not meaningful by themselves. The block also stores its scale and offset once. When a code is used, that shared metadata maps it back to an approximate value. Together, our tiny teaching block needs 7 bytes. With 64 weights, FP16 needs 128 bytes. Q4 needs 32 bytes of codes plus 4 bytes of metadata. The metadata cost is shared across the block. Real files still include headers and some higher precision tensors, so the saving is not exactly 4 times. Before scaling this mechanism to a whole model, we can now decode the familiar FP16, Q8, and Q4 labels. Before scaling beyond our teaching block, compare the storage choices directly, keep the same tensor shape and the same weight positions, change only what bits are stored at those positions. In FP16, every weight carries its own 16-bit floating point encoding. This is our larger baseline without shared Q4 style codes or a local group ruler. With Q8, each position instead stores an 8-bit code. A group also stores metadata that maps its 256 possible codes onto a real number range. With Q4, each position stores a 4-bit code, so 2 codes fit in 1 byte. The same tensor is smaller, but each local ruler offers only 16 landing points. Now we can ask how real tensors share those rulers. A real model cannot use one ruler for billions of varied weights. Quantizers divide tensors into blocks or groups, and each group receives its own scale and offset. That lets one region use a narrow, fine ruler while another covers a wider range. The metadata is local, only the weights in that group use it. Smaller groups usually preserve more local detail because fewer weights must agree on one range. The cost is storing more scales and offsets across the tensor. Larger groups reduce metadata overhead, but more varied weights must share one ruler. That creates the next question immediately. What happens when one unusually large value stretches the shared range for all of its neighbors? Start with one ordinary group. Its weights run from about negative 0.9 to positive 1.1. Divide that range across the 15 gaps between 16 Q4 codes, and the scale is roughly 0.13. In plain language, adjacent codes represent values about 0.13 apart. Now place one unusually large weight, positive 3.4, inside the same group. We still have only 16 codes, but their ruler must stretch from negative 0.9 all the way to 3.4. The scale grows from 0.13 to 0.29, so adjacent codes are now more than twice as far apart in real value. The ordinary weights now occupy only the left part of that wider ruler, so several of them compete for roughly 7 useful codes and may snap farther. Smaller groups do not remove the outlier, but they limit how many neighboring weights must share its coarse range. Other groups keep their final rulers, pause, and connect the complete mechanism. Real weights become small codes. Scale and offset interpret those codes locally. Fewer bits reduce storage, while group range determines how far apart the landing points are. Outliers can widen that range, and smaller groups can limit the damage. We now know where approximation error comes from. Next, we ask which errors actually matter to the trained model's behavior. Before naming methods, place them on the map. Quantization can target stored weights, temporary activations, or the growing KV cache. The downloadable model files we are investigating mainly quantize the first branch, weights. When those weights come from a model that has already finished training, converting them afterward is called post-training quantization, or PTQ. A small calibration sample may help choose better ranges or rounding decisions. The full training process is not repeated. Weight PTQ keeps the trained tensor structure and converts its exiting values into lower bit codes and metadata. GPTQ and AWQ sit under this umbrella. There are two strategies for deciding which quantization errors are acceptable. We will separate them, beginning with GPTQ's focus on preserving a layer's output. These are the same small codes we created earlier. Each code reconstructs an approximate weight. Simple rounding tries to keep each reconstructed weight close to its original value. GPTQ looks at what those approximations do together. Take two weights acting on a simple input. The originals add to 1.0. Their reconstructed values are each off by 0.1, yet one error is high and the other is low, so the output still adds to 1.0. This cancellation is only an intuition, not a pair that GPTQ deliberately searches for. On representative inputs, GPTQ compares the layer's original output with the output produced by reconstructed weights. GPTQ commits weights to codes in sequence. When those reconstructed weights shift the layer output, information from the sample inputs guides updates to weights that have not yet been quantized. The goal is to reduce the output error introduced so far. AWQ keeps the same post-training setting but asks a different question: which channels carry the strongest useful signal? AWQ stands for Activation Aware Weight Quantization. It uses a different signal: activations produced by sample inputs as they flow through the model. Some channels consistently light up much more strongly. Their associated weights have greater influence on the layer's useful behavior. AWQ uses that activation evidence to rescale salient channels so their low bit approximation causes less damage. GPTQ watches output error. AWQ watches which channels carry important signal. Both are post-training quantization, but their evidence and visual logic are different. So far, we have focused on checkpoint weights. Now we can return to the other numerical states we saw at the beginning. Weights explain the checkpoint, but quantization is broader. Temporary activations can also use lower precision during serving. The KV cache grows with prompt length, generated tokens, and concurrent users. Quantizing targets a different runtime memory problem. For fine-tuning, techniques such as QLOW-RA keep a low-bit base model frozen, while small trainable adapters receive updates. None of this guarantees speed. Performance depends on kernels, dequantization, batching, and whether the hardware supports the format efficiently. With that context, you can return to the download shelf and evaluate the files as deployment choices, not just bit labels. Now return to the download shelf with a useful mental model. FP16, Q8, and Q4 describe representation choices. GPTQ and AWQ describe quantization approaches. GGUF describes a container and runtime ecosystem, not one universal quantization method. Before choosing, check model fit, quality on your prompts, actual speed, context memory, runtime support, and what was quantized. Quantization is not merely making an LLM smaller. It is choosing which numerical approximations your complete workload can afford. If this made quantization clear, subscribe. We will keep opening up the systems behind modern AI, one mechanism at a time.